Hello friends, in this class we are discussing the electrical properties of solids. Based on their electrical conductivity, solids can be classified as conductors, insulators and semiconductors. Conductors means the solids through which electricity can flow to a large extent are called conductors. Simply we can say that they can conduct electricity. The electrical conductivity of metals lies between 10 raised to 6 to 10 raised to 8 ohm inverse centimeter inverse. The insulators means they do not allow the passage of electricity and their conductivity order is 10 raised to minus 12 ohm inverse centimeter inverse. Then semiconductor means the conductivity lies between metals and insulators. Their conductivity increases with the temperature and the order is 10 raised to 2 to 10 raised to minus 9 ohm inverse centimeter inverse. Now I am going to discuss the theory of how different metals have different conductivity. Okay. The conductivity of metals depend upon the number of valence electrons. So when we are going to talk about the conductivity of different metals, we should know two terms, that is the valence band. The second one is the conduction band. Valence band means the bands are formed by valence electrons. That is called valence band. So it is the highest occupied band. Then the conduction band means the band just above the valence band. It is the lowest occupied band. So based on these two bands, we can say why some metals have good conductivity and why others do not have conductivity. Okay. So based on this diagram, we can simply explain why metals are conductors and insulators are non-conductors. Okay. First we can consider metals or conductors. We know that all metals are conductors. So this is the conduction band and this is the valence band. Okay. Valence band is partially filled or overlapping between valence band and conduction band. So in this case, there is an overlap between valence band and conduction band. So electrons present in the valence band can easily go through the conduction band. So this movement is responsible for the conductivity. So in the case of conductors, this movement of electrons from valence band to conduction band is very easy. That's why the metals are conductors. Okay, I hope you understand. The next one is semiconductor. In the case of semiconductor, this is conduction band and this is valence band. So the gap between the valence band and the conduction band is called a forbidden zone. So in the case of semiconductors, the energy gap is very small. So this gap is very small. When increase the temperature, it gives thermal energy to the electrons and it can move conduction band to valence band. So in the case of semiconductors, this energy gap is very small. So when we are applying temperature, the valence electrons will get thermal energy and it can easily go through the conduction band and it will become conductors. Okay. So in the case of insulators, the conduction band and valence band energy gap is very high. So the electrons presented in the valence band cannot move through the conduction band even when we are applying a temperature. Okay, this is why the insulators are non-conductors. I hope you understand. So we have detailedly discussed why some metals are conductors and why others are non-conductors. So then we are going to look for semiconductors. Actually this topic is very important. We all know that the energy gap is very small in semiconductor and when we increase the temperature, it gives thermal energy for some of the electrons in the valence band to move the conduction band. Okay, and it became conductors. So electrical conductivity is in between insulators and conductors. So in semiconductor, the electrical conductivity lies between insulators and conductors. And when the temperature is increases, their conductivity will increases. This semiconductor. So we all know that semiconductors are generally group 14 elements. The examples are germanium and silicon. Okay. This semiconductor can be classified into two. They are intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductors means the semiconductivity of elements are due to their structure, because the structure itself gives it some conductivity. That kind is called intrinsic semiconductor. The extrinsic semiconductor means the semiconductivity of intrinsic semiconductor can be enhanced by the addition of small quantities of impurity and is called extrinsic semiconductor. So, extrinsic semiconductor means we all know that the semiconductors are not good conductors. That's why we are doing some modifications to increase its conductivity. And one modification is we are adding some impurities to this intrinsic semiconductor, and which will increase its conductivity. And when we are adding the impurities to enhance its conductivity, that process is called doping. Okay, I hope you understand. When we are adding group 15 elements to our normal semiconductor, it is called N-type. And when we are adding group 13 elements, it is called P-type semiconductor. So the classification of N-type and P-type is very important. Now we are going to discuss about the characteristics of N-type and P-type semiconductor. N-type means the phosphorus and arsenic, that is group 15 elements, enter inside the crystal lattice of germanium or silicon, that is group 14. It means germanium or silicon is our intrinsic semiconductor, and we are adding some impurities like phosphorus and arsenic into it. Okay. So by replacing them from the lattice point, it is called N-type semiconductor. It means when we are adding phosphorus or arsenic into the intrinsic semiconductor, that type of semiconductor is called N-type. Okay. The excess valence electron is formed after forming 4 covalent bonds. The excess electron will give an electronic conduction. Okay, its diagram is like this, because this silicon is our normal intrinsic semiconductor and its valence is 4. 1, 2, 3, 4. When we are adding an impurity like phosphorus, its valence is 5. So it will form 4 covalent bonds with silicon, and also 1 free electron will be here because its valence is 5. Phosphorus valence is 5. 1, 2, 3, 4, 5. So the 5th electron will be a free electron, and it will give conduction to our semiconductor. I hope you understand. Okay. The another one is N-type, P-type semiconductor. In this case, the aluminium and gallium, that is the group 13 elements, can enter the germanium or silicon, group 14, in a crystal lattice by replacing them from the lattice point. It forms 1 electron deficient or hole. This gives positive hole conduction. So it means that its diagram is like this. So the silicon is our normal intrinsic semiconductor and its conductivity is 4. Okay. And when we are adding an impurity like aluminium, its valence is 3. So 3 aluminium electrons will form covalent bond with 3 other silicon atoms. 1, 2, 3. Okay. And the 4th one will be a hole. There is no electron in the aluminium, so it will appear as a hole. And this hole we can consider as a positive charge. This hole we can consider as a positive charge. And this hole will give conduction to our semiconductor, and this type semiconductor is called p-type semiconductor. I hope you understand. The next one is magnetic properties. The magnetic properties of substance are associated with the electrons. Depending on the behavior in the magnetic field, solids can be classified into the following. The first one is diamagnetic substance. These substances are weakly repelled by the magnetic field because they do not have any unpaired electron. So diamagnetic substances do not have any unpaired electrons. That's why they are weakly repelled by the magnetic field. The examples are NaCl, TiO2, NH3 and benzene. The second one is paramagnetic substance. They are attracted by the magnetic field and they have unpaired electrons. So the paramagnetic substances are attracted by the magnetic field because they have unpaired electron. They lose magnetism in the absence of magnetic field. Okay. The examples are O2, CuO, Fe3+, Al, Mn, NO, etc. So this is the diagram of diamagnetic substance and paramagnetic substance. Okay. The next one is ferromagnetic substance. It means substance which are strongly attracted by a magnetic field. They show the magnetic behavior even when the external magnetic field is removed. So ferromagnetic substance means they are strongly attracted by the magnetic field. Even when we are remove the external magnetic field, they will show the magnetism. The examples are Fe, Co, Ni, CrO2 and gadolinium. Okay, the other one is antiferro and the alignments are like this. The alignment of magnetic momentum is like this. Okay. The other one is antiferromagnetic substance. It means these substances possess paramagnetism or ferromagnetism on the basis of unpaired electron. But actually they possess zero magnetic moment. Okay. This is called antiferromagnetic substance. So based on the unpaired electron, we may assume that they will show paramagnetic or ferromagnetic behavior. But actually their net magnetic field is zero. Net magnetic moment is zero. Because in such a substance, the half of the magnetic moments are aligned in one direction and other half in the opposite direction. Okay. This is why they show zero magnetic moment. Look here, half of the magnetic field are aligned, half of the magnetic moment are aligned in one direction and other are in the opposite direction. That's why they have zero magnetic moment. The example is MnO. The next one is ferrimagnetic substance. It means these substances which are expected to possess large magnetism on the basis of unpaired electrons, but actually have small net magnetism. This is due to the alignment of the magnetic moment in opposite direction in unequal numbers, resulting in a net magnetic moment. So the ferrimagnetic substance means they also have some unpaired electrons. So we may expect they have large magnetism, but actually they possess only small magnetism. Okay. In the case of antiferromagnetic substance, the net magnetic moment is zero. But here it has some magnetic moment, but it is very small. That it is because this is due to the alignment of magnetic moments in opposite direction in unequal number. Because then unequal number. If the numbers are equal, then the magnetic moment will be zero. Here it is unequal and it is resulting in a net magnetic moment. The examples are Fe3O4, MgFe2O4. Then another important point is Curie temperature. Curie temperature means it is the temperature at which the ferro, antiferro and ferrimagnetic substance became paramagnetic. It is called Curie temperature. Thank you, students.